Hello everyone, my name's Iman. Welcome back to my YouTube channel. In today's lesson, we're going to discuss reaction mechanisms and catalysts. But before we do that, I want to briefly summarize the most important ideas from our last lecture on rate laws, because everything we've learned there serves as the foundation for understanding how mechanisms determine the rate of a reaction. The table you see here brings all of those ideas together in one place. It reminds us that the differential rate law tells us how the instantaneous rate depends on concentration. For a zero-order process, the rate equals K, and it doesn't depend on how much reactant you have. For a first-order reaction, the rate equals K multiplied by the concentration of A, so the rate changes directly with concentration. And for a second-order reaction, the rate equals K multiplied by the concentration of A squared, or by the product of two concentrations, depending on the system. Each of these expressions tells us how sensitive the rate is to changes in concentration. From there, we connected the differential form to the integrated rate laws, which describe how concentration changes as time passes. For a zero-order reaction, the integrated form tells us that the concentration at time t equals the initial concentration minus K times T. And this produces a straight line when we plot concentration versus time. The slope of this line gives us negative K. For first-order kinetics, the natural log of the concentration at time t equals the natural log of the initial concentration minus K times T. And plotting the natural log of concentration versus time gives us a straight line with a slope of negative K. For second-order reactions, 1 divided by the concentration at time t equals 1 divided by the initial concentration plus K times T. And this becomes a straight line when we plot the reciprocal of concentration versus time. The slope here gives us positive K. These straight line plots are powerful because each reaction order becomes linear only when the correct transformation is used. So choosing the right axes immediately reveals the order of the reaction. We also talked about how the rate responds when we change the concentration. So for instance, in a zero-order reaction, the rate stays the same no matter how much reactant you add. In a first-order reaction, the rate changes in direct proportion to concentration. So if you double the concentration, you double the rate. You triple the concentration, you triple the rate. In a second-order reaction, the rate changes with the square of the concentration. So if you double the concentration, the rate increases by 2 squared, or it quadruples. If you triple the concentration, then the rate increases by 3 squared. So it increases by a factor of 9. And this behavior helps us interpret data tables and determine reaction orders by comparing how the rate changes between trials. Another important idea from last time was how the half-life behaves. For a zero-order reaction, the half-life depends on the initial concentration, and it becomes shorter as the reaction proceeds. For a first-order reaction, the half-life is constant, which means it does not depend on the starting amount at all. And then for a second-order reaction, the half-life increases as the reaction continues because fewer molecules remain to collide and react. Finally, we emphasize that the units of the rate constant K serve as a quick diagnostic tool. If K has units of molarity per second, the reaction is zero order. If K has units of per second, then the reaction is first order. And if K has units of 1 over molarity seconds, the reaction is second order. And when we put all of this together, we have a complete kinetic picture. We know how the rate depends on concentration. We know how concentration changes with time. we know how the half-life behaves, and we know how to determine the rate constant experimentally. Before we transition into mechanisms, I want to spend a moment reviewing how we extract information from straight line plots. In the last lecture, we focused on either looking at the rate constant units or using the method of initial rates. But now it's time to look at the plots. And this is a crucial skill because so much of kinetics relies on recognizing which plot becomes linear and then using that line to determine the rate constant. Any straight line follows the familiar equation y equals mx plus b. In that form, y is the dependent variable on the y-axis, x is the independent variable on the x-axis, m is the slope, and b is the y-intercept. All of the integrated rate laws were rearranged to match this format, and that is exactly why we can determine rate constants from experimental plots. Once the data form a straight line, the slope is going to directly correspond to the rate constant k, either as positive or negative k, depending on the reaction order. Let's walk through a couple of examples. The first question asks, what must be plotted to obtain a straight line that yields a rate constant of 0.1 per second? Since the units of k are per second, we immediately know that this is a first order reaction. For a first order process, the integrated rate law tells us that the natural log of the concentration of A equals the natural log of the initial concentration minus k times t. This matches y equals mx plus b when we plot the natural log of concentration on the y-axis and time on the x-axis. So to obtain a straight line whose slope is negative 0.1 per second, we have to plot the natural log of the concentration versus time. Now let's look at the second example here. A researcher plots 1 divided by the concentration of A versus time and obtains a straight line. They observe that the y-intercept is 5 millimolar. What was the initial concentration of the species? Well, a straight line from a 1 over concentration versus time plot tells us immediately that the reaction is second order. For a second order reaction, the integrated rate law has the form 1 over the concentration at time t equals 1 over the initial concentration plus k times t. If we compare this to y equals mx plus b, the y-intercept corresponds to 1 over the initial concentration. So if the y-intercept is 5 millimolar, that value represents 1 divided by the initial concentration. Taking the reciprocal gives us an initial concentration of 0.2 millimolar. Now that we understand how to analyze kinetic data and how rate laws behave for different reaction orders, we're ready to take the next step and connect these ideas to the energy landscape of a reaction. To do that, we need to talk about reaction profiles again. We briefly touched on this 2 lectures ago, but it's definitely worth revisiting. These diagrams give us a visual picture of how the energy changes as reactants move towards products, and they really help us connect kinetic observations like rate constants and activation energies to the molecular story that's happening. A reaction profile is going to plot energy on the y-axis and reaction progress on the x-axis. And when we look at a diagram like this one, the very first value represents the reactants and the final represents the products. Everything that happens in between, every rise and fall, corresponds to the pathway that the system follows as bonds break and new bonds form. The peaks you see here are the transition states. A transition state is the highest energy point along each step of the reaction. So it represents an extremely short-lived, unstable arrangement of atoms that sits right at the top of the energy barrier. Because these transition states are so high in energy, they are the hardest configurations for the system to reach. And that is why the height of each peak corresponds to the activation energy of that step. In this diagram, the first rise takes the reactants up to the first transition state. Then the system falls into a valley that represents an intermediate. An intermediate is a species that actually exists for a brief period of time during the reaction. It has a definable structure and a finite lifetime, and it can be isolated and studied, unlike the transition states. The system then climbs a second energy barrier to reach the second transition state before finally reaching the products. One of the most important pieces of information we extract from these profiles is the relative size of the activation energies. The step with the largest activation energy is going to be the slowest step, and that step becomes the rate determining step. This is a key idea because it connects the shape of the energy profile to the kinetics that we measure experimentally. The tallest energy barrier acts like a bottleneck. No matter how quickly the other steps occur, the reaction can't proceed faster than its slowest step. And understanding reaction profiles gives us the foundation we need to interpret mechanisms more deeply. Now that we can visualize how energy changes from one step to the next, we can start to explore how real reactions proceed through a sequence of elementary steps and why the overall rate law reflects the step with the highest barrier. With that in mind, let's finally discuss what a reaction mechanism actually is and why the balanced chemical equation almost never tells the full story of how reactants turn into products. A reaction mechanism is the detailed step-by-step pathway that reactants follow as they transform into products. It breaks the overall reaction into a sequence of elementary steps, and each step represents a single molecular event, such as a collision or a bond rearrangement. When we look at a balanced chemical equation, the overall equation only tells us what we start with and what we end with. It doesn't show the individual steps that occur along the way. And because the rate law depends on which step is slowest, that's the step we write the rate law for, we can't just rely on the coefficients from the overall balanced reaction to determine the rate law. Instead, the rate law must come from the mechanism itself. With that being said, let's revisit an example that we saw earlier in our lectures. Suppose we have the overall reaction A2 plus 2B forming 2AB. From the balanced equation, it might look like everything happens in one smooth step. But in reality, the reaction occurs in two elementary steps. In the first step, A2 reacts with just one molecule of B to form an intermediate called A2B. And this step is the slowest. This step is the rate determining step. In the second step, that intermediate A2B reacts with another molecule of B to finally form the 2AB products. And this step is fast. Now, even though the overall reaction consumes 2B molecules, this mechanism shows us that they're not used at the same time. And the slow first step is the one that determines the rate. Here's another example. Nitrogen dioxide reacting with carbon monoxide to form nitrogen monoxide and carbon dioxide. Experimental evidence shows that this reaction happens in two steps. In the first step, nitrogen dioxide reacts with another nitrogen dioxide molecule to form nitrogen trioxide and nitrogen monoxide. Then in the second step, nitrogen trioxide reacts with carbon monoxide to produce nitrogen dioxide and carbon dioxide. And when we add these two elementary steps together, the intermediate nitrogen trioxide cancels out because it appears once as a product and once as a reactant. And this leaves us with the overall balanced equation that we started with. This example illustrates two important ideas. First, the overall reaction is simply the sum of all of the elementary steps in the mechanism. And second, any species that's formed in one step and then consumed in a later step is called an intermediate. Intermediates don't appear in the overall reaction, but they do play an important role within the mechanism. By the way, this is in contrast to catalysts. A catalyst appears as a reactant in an early step, and then it's regenerated in a later step. Catalysts, they speed up the reaction by lowering the activation energy of one or more steps, but they're not consumed over the course of the reaction. Then the next question is, well, how do we use this mechanism to determine the rate law? And for this example, there's two possible scenarios depending on which step is slow. Let's go through each one and see how the rate law emerges from the mechanism. So let's go back to our mechanism and let's consider the two scenarios. In the first scenario, let's say that step one is the slow step. If that is the case, how do we write the rate law for this reaction if step one is the rate determining step? Well, step one shows two molecules of nitrogen dioxide combining to form nitrogen trioxide and nitrogen monoxide. And the rate law is going to come directly from the reactants for this step. So we're going to write rate equals K, the rate constant, multiplied by the concentration of nitrogen dioxide, multiplied by the concentration of nitrogen dioxide again, which simplifies to K times the concentration of nitrogen dioxide squared. This situation is straightforward because the slow step involves only reactants that appear in the overall reaction. So we don't have to worry about intermediates. Therefore, writing the rate law based off of this slow step is perfectly fine as is, and there's nothing else we have to do. Now, in the second scenario, things get a little more complicated. In the second scenario, we're going to actually pretend that step two is the slow step, not step one. Step two shows nitrogen trioxide reacting with carbon monoxide to form nitrogen dioxide and carbon dioxide. Again, because this is an elementary step, the rate law would be written as K, the rate constant, multiplied by the concentration of nitrogen trioxide, multiplied by the concentration of carbon monoxide. But now we have a problem. This isn't good enough because in this rate law, we have nitrogen trioxide. Nitrogen trioxide is an intermediate, and intermediates are not allowed to appear in the final rate law. The rate law must be written only in terms of species that appear in the overall balanced reaction. So then the question becomes, how do we get rid of the intermediate? To do that, we need to use the fast step. So in this mechanism, we said step two is slow, step one is fast. Step one is fast, and fast steps often act like pre-equilibria, meaning the reactants and the products of that step establish a relationship that we can use. So that means we're going to now focus on step one so that we can get an alternative expression to replace this nitrogen trioxide term in our rate law. Now, the equilibrium constant for step one is going to help us do that. Step one shows us that nitrogen dioxide reacts with nitrogen dioxide to form nitrogen trioxide and nitrogen monoxide. Because this step is fast, we're going to write an equilibrium expression. The equilibrium constant for step 1 is going to equal the concentration of nitrogen trioxide multiplied by the concentration of nitrogen monoxide, all divided by the concentration of nitrogen dioxide squared. If we rearrange this equation to solve for the concentration of nitrogen trioxide, we find that the concentration of nitrogen trioxide equals the equilibrium constant multiplied by the concentration of nitrogen dioxide squared divided by the concentration of nitrogen monoxide. Now, we can substitute this expression for nitrogen trioxide back into our rate law. When we replace the concentration of nitrogen trioxide with this new expression, the rate becomes equal to the rate constant multiplied by the equilibrium constant multiplied by the concentration of nitrogen dioxide squared multiplied by the concentration of carbon monoxide divided by the concentration of nitrogen monoxide. Now the constants, they can be combined into a new constant, which we call K prime. So the final rate law becomes K prime multiplied by the concentration of nitrogen dioxide squared multiplied by the concentration of carbon monoxide, all divided by the concentration of nitrogen monoxide. And this gives us a rate law that no longer contains the intermediate, and it's written entirely in terms of measurable species found in the overall reaction. With that, we're ready to move into our last topic and look at 3 catalytic processes that have enormous real-world importance. Now, a catalyst is defined as a substance that provides an alternative reaction pathway with a lower activation energy. And so it allows the reaction to proceed more quickly without being consumed in the overall process. So in other words, the catalyst participates in the mechanism, but it is regenerated by the end of it. The ozone layer, the exhaust system in a car, and the industrial production of ammonia all rely on catalysts to transform reactants efficiently. So as we walk through the ozone layer decomposition, Cadillac converters in automobiles, and the Haber process, we're going to identify the specific catalyst involved, and we're going to see exactly how it accelerates the reaction. The first example is ozone layer decomposition. This process uses a homogeneous catalyst, which means the catalyst is in the same phase as the reacting gases. In this case, the catalyst is the chlorine radical, written as Cl dot. Chlorine radicals are formed in the upper atmosphere when UV light breaks apart chlorofluorocarbons, or CFCs. These compounds were once widely used in refrigeration systems and aerosol products. When UV radiation strikes a chlorofluorocarbon molecule, it's going to go ahead and break the carbon-chlorine bond, and it releases a chlorine radical. Once a chlorine radical is present, it immediately enters a catalytic cycle that destroys ozone. In the first step, the chlorine radical reacts with ozone to form chlorine monoxide and oxygen gas. In the second step, the chlorine monoxide reacts with a free oxygen atom to regenerate the chlorine radical and produce more oxygen gas. And when we add these 2 elementary steps together, the chlorine radical cancels out because it's consumed in one step and then regenerated in the next. And that is the defining behavior of a catalyst. Now, it participates in the mechanism and it accelerates the reaction by lowering the activation barrier. And then it reappears unchanged at the end. Here, The chlorine radical really speeds up the decomposition of ozone without being consumed, and the net effect converts 2 molecules of ozone into 3 molecules of oxygen gas. The concern here is that a single chlorine radical can complete this cycle thousands of times before it's finally removed from the atmosphere. And this catalytic chain reaction was directly responsible for the thinning of the ozone layer, particularly over Antarctica. And once scientists understood the mechanism and they recognized how efficiently chlorofluorocarbons were breaking down ozone, international agreements were put into place to try to phase out their use and really protect the ozone layer from any further damage. The second major catalytic system we rely on every day is the catalytic converter that's found in automobile exhaust systems. This device uses a heterogeneous catalyst, which means the catalyst is actually in a different phase than the reacting gases. In this case, the catalyst is a solid surface that's composed of platinum and palladium metals. And so as hot exhaust gases flow over this metal surface, the catalyst provides a place for several important reactions to occur. One of the key reactions is the reduction of nitrogen oxides. These nitrogen oxides are formed during high temperature combustion in the engine. When they contact the catalyst surface, they gain electrons and they are reduced to form harmless nitrogen gas. At the same time, the catalyst promotes oxidation reactions. Carbon monoxide and unburned hydrocarbons from the fuel are oxidized on the metal surface to form carbon dioxide and water. These oxidation and reduction steps happen rapidly because the catalyst lowers the activation energy for the reactions and it allows them to happen efficiently even at the short time scale of engine exhaust flow. Because of this, catalytic converters dramatically decrease the amount of harmful pollutants that are released into the atmosphere. In fact, they are considered one of the most effective environmental technologies ever implemented. When we combine all of the steps that occur inside the converter, the overall effect is that nitrogen oxides, carbon monoxide, and hydrocarbons are converted into nitrogen gas, carbon dioxide, and water. And these are substances that are far less damaging to air quality. The final catalytic process we're going to look at is the Haber process, which is one of the most important industrial reactions on Earth. This reaction takes nitrogen gas from the atmosphere and it converts it into ammonia. Ammonia is the foundation of most fertilizers used in agriculture. So the ability to produce it on a large scale has allowed us to support food production for billions of people. Without the Haber process, modern agriculture would not exist in the form that we know today. The catalyst that's used in the Haber process is a slightly oxidized iron powder. This makes it another example of a heterogeneous catalyst because the catalyst is a solid while the reactants are gases. The iron surface provides a place where nitrogen and hydrogen molecules can attach, weaken their bonds, and react more easily. And this is very important because nitrogen gas is extremely stable. The nitrogen to nitrogen triple bond is one of the strongest bonds in all of chemistry, and breaking this bond requires a very large amount of energy. And that is why nitrogen does not react readily on its own. When nitrogen molecules bind to the iron surface, the catalyst helps stretch and weaken the triple bond. And this lowers the activation energy and it makes it much easier for hydrogen molecules to add and form ammonia. And the overall reaction is really simple to write. Nitrogen gas reacts with 3 molecules of hydrogen gas to form 2 molecules of ammonia. But even though the reaction appears simple, it doesn't proceed at a useful rate without the help of the catalyst. The kinetic barrier that's associated with breaking that nitrogen triple bond is just too high. So the iron catalyst is super essential for making the reaction feasible. And industrial plants that run the Haber process, they operate at high pressures and moderately high temperatures. And these conditions really help shift the equilibrium towards ammonia formation while still keeping the reaction fast enough to be practical. And so the combination of optimized reaction conditions and a highly efficient iron catalyst is really what allows the Haber process to run on a massive scale and produce hundreds of millions of tons of ammonia every year. Before we end this lesson, let's just do a quick concept check. This problem asks us which of the following catalytic processes employ heterogeneous metal catalysts. Let's go through each option. Statement 1 says the Haber process to produce ammonia. The Haber process uses a solid iron catalyst, so that one is heterogeneous. Statement 2 says the Catalytic converter in automobiles. The Catalytic converter also uses solid metals, platinum and palladium, so that is another heterogeneous catalytic system. Statement 3 says ozone decomposition. Now, ozone decomposition actually involves chlorine radicals in the gas phase, which means it is homogeneous, not heterogeneous. So the processes that use heterogeneous metal catalysts are the Haber process and the Catalytic converter, which is statement 1 and 2. That means the correct answer is going to be B. With that, we've completed this lecture. I hope it helps. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.